Good morning. We are the students of ComSats University Islamabad, WA campus. We are final year students of electrical engineering. I'm Ali Said, bearing registration number FA21 BEE075, and my fellow group member is Nismat Abid, bearing registration number FA21 BEE073. Today we are here to present our final year project. We are doing this project under supervision of our hardworking professor, Ma'am Maliha Amjad. Our project title is AI-Driven Energy Optimization Balancing Solar and Utility Power. Introduction. As the world moves towards renewable energy, managing the unpredictable nature of solar power becomes essential. Our system uses AI to balance power from solar panels, utility sources, and batteries to ensure efficient, cost-effective, and reliable energy use. Project Overview. The main objective is to reduce electricity bills by maximizing solar energy usage and minimizing grid dependency. Our system automatically manages the energy mix by analyzing data and switching sources accordingly. For example, if solar energy is low during cloudy hours, it shifts to battery or utility power without manual intervention. Scope. Our system not only controls but also predicts solar generation and electricity usage patterns. With real-time data, it dynamically decides the most cost-effective source of power. This makes it ideal for smart homes or microgrids where managing energy cost and availability is crucial. System Overview. Raspberry Pi-based controller. At the core is a Raspberry Pi, which serves as the brain. It collects data from multiple sensors and uses machine learning to make decisions. It controls when to switch between solar panels, battery, and utility power, ensuring optimal performance and minimal energy waste. AI-based prediction model. We use machine learning models like decision trees that are trained using both historical and real-time data. These models forecast solar availability based on weather conditions and predict household energy demand. This helps preemptively decide whether to rely on solar, battery, or utility. Implement strategy. We use Sensor to gather live data. DHT11 for temperature and humidity, ZMPT101B for voltage sensing, ZMCT103C for current sensing, and Solar Sensor to measure sunlight intensity. Real-time data is collected from DHT11, ZMCT103C, and ZMPT101B sensors. Raspberry Pi collects this data continuously for monitoring power generation, load, and environmental changes. Historical and real-time data are both used to train AI models. Machine learning algorithms like decision tree predict solar availability and load demand. Based on prediction, the system automatically switches power sources. Conclusion. The project develops an AI-driven energy management system to optimize power usage between solar and utility sources, addressing solar intermittency and fluctuating utility costs. Using Raspberry Pi, the system predicts solar generation and energy demand, dynamically switches between power sources, and provides real-time optimization. This solution aims to reduce costs, enhance sustainability, and minimize grid reliance. Solar panel converts sunlight into DC electricity. This energy is stored in a battery through a charge controller, which also protects the battery from overcharging. The battery stores solar energy and provides power when solar or utility sources are unavailable. The inverter converts the battery's DC output to AC for powering household loads. The system uses various sensors to monitor voltage, current, temperature, and WAPDA availability. A temperature sensor monitors ambient temperature, while an optocoupler detects the presence of AC utility power and provides electrical isolation. A DC, analog to digital converter, converts analog sensor data, like voltage or temperature, into digital signals so the Raspberry Pi can process them. Machine learning models such as decision tree, DTT, are used for solar energy forecasting, load prediction, and analyzing battery status. These models help decide whether to use solar or WAPDA based on data inputs. Raspberry Pi GPIO pins cannot directly drive relays due to current limitations. Therefore, a transistor-based relay driver circuit is used. MOSFETs amplify the control signals and handle power switching. Diodes protect the circuit from back EMF during relay switching. Pulse width modulation, PWM, is used to control charging and switching operations efficiently. LCD displays real-time information such as battery charging status, current power source, solar or WAPD, and other system states. When the system is powered on, it begins monitoring the availability of both solar energy and the utility supply, WAPDA. The energy source selection is made dynamically based on their availability. Primary source, the WAPDA. If solar energy is not available and WAPDA is present, the system automatically connects to WAPDA to power the load. Fallback to battery. In the event that WAPDA is also unavailable and there is no solar input, the system intelligently shifts to the battery as a backup power source, ensuring continuous power supply. Solar as priority source. If WAPDA is unavailable and solar energy is present, the system switches to solar power. The solar panel powers the load directly or via battery, depending on the configuration. The switching between sources is managed by the Raspberry Pi through relay-based circuits, ensuring a seamless transition without interrupting the load. This intelligent source selection is based on real-time inputs from voltage, current, and utility detection sensors, providing reliability and energy efficiency.